Alright, so let's look at an example involving some calculations using this equation. So let's say you're sitting in your car listening to 101.7, which is going to be a kilohertz. You're waiting for a red light, which has a 700 nanometer wavelength. You're waiting for that to change so you can go. And you have the window rolled down and you're absorbing the UV rays from the sun, which are going to be at 200 nanometers. So let's say I want to determine the wavelength in nanometers of the radio station I'm listening to. How am I going to do that? Well, keep in mind, wavelength times frequency equals at C, or 3.00 times 10 to the 8th meters per second. Also keep in mind, 1 hertz is equal to 1 per second. So all I need to do is plug my values in to this equation. Well, what don't I know? I don't know wavelength. That's what I want to find. I know frequency, so I plug my frequency in. Now keep in mind, my frequency is in kilohertz. I'm going to get it in that per second, so 101.7 kilohertz is 101.7 times 10 to the 3rd hertz, which is equal to 101.7 times 10 to the 3rd per seconds. Right? So the only thing I don't know is wavelength. Solve for wavelength, I get 2.95 times 10 to the 3rd meters. Very, very important here. Make sure wavelength is going to be in meters, frequency is going to be in that per seconds, or hertz, because my units on my speed of light constant is meters per second. Those units have to agree so they cancel out properly. So when I solve for wavelength, I get my units in meters. Well, the question's asking for nanometers, so then I need to convert it from meters to nanometers. So I end up with 2.95 times 10 to the 12th nanometers. That's the wavelength of the radio station I'm listening to. Okay, so let's now look at the frequency of the red light I'm waiting on. So I want the frequency in hertz. Well, keep in mind my equation, my relationship, wavelength times frequency equals speed of light. Keep in mind that 1 hertz is equal to 1 per second. Fill in what I know. Now in this case, my wavelength of my red light is given to me in nanometers. I need to get that to meters to agree with my units so they cancel. So when I put it in, I can put 700 times 10 to the negative 7th meters. I do that just as a quick way to write it. Technically it should be 7.00 times 10 to the negative 7th meters, but either way will work. Okay, but that wavelength times frequency equals the speed of light. Solve for frequency. I get it in a per second unit, but the per second and the hertz are interchangeable, so it just becomes my hertz. Alright, let's calculate it for the UV rays. So I've got my equation and my relationship. Substitute things in, solve for my frequency, convert it to hertz. Okay, these are pretty straightforward calculations. The biggest thing to remember is you've got to keep track of the units. You've got to make sure those units agree with the units on the speed of light. So we've been talking about electromagnetic radiation, doing those calculations. We're going to get talking a little bit more about some issues between matter and light that are confusing for us. When we discuss these things, it's going to help us better understand those electrons in the atoms and better understand this relationship between light and matter. Okay, so we're going to talk about 3 things. We're going to talk about black body radiation first, and then we're going to talk about something called the photoelectric effect, and then we're going to deal with emission spectra. These 3 things are going to help us understand the relationship between light and electrons and atoms a lot better. So first up, black body radiation. Well, what is it? Well, black body radiation is the fact that certain materials, when heated, are going to produce light. If we look at smoldering coal, coal is basically carbon. When it's heated, when it's started to burn, it produces that light. We see that light coming off. We also see from an electric heating element, we see light coming off of it as we heat it up. And then with a light bulb, it's just a filament inside an evacuated chamber. Pass current through it, it heats up, it emits that white light. What this helps us understand, though, is because as we're getting this thermal energy put in, we're getting this light out, and it's starting to help us see a relationship between energy and light, and energy and color, or more importantly, the wavelengths of light. So when we're dealing with energy, we can now come up with a new relationship where energy is going to be equal to H times V, V being that frequency. All right, now if I look at my wavelength times frequency equals C, and I solve for frequency, plug that in, I'll get C over lambda, so energy could also be equal to HC over lambda. Okay, it's just a rearrangement of the 2 equations. But with H is going to be something called Planck's constant. And the value of Planck's constant is going to be 6.626 times 10 to the negative 34th joule seconds. Note, it's joules times seconds, it's not joules per second. Okay, it's joules times second. That's Planck's constant. So if I know a color has a certain frequency, and I want to know the energy associated with that color, take that frequency times Planck's constant. If I know a wavelength of a certain color, I could take hc divided by that wavelength and get the energy associated with it. Keep in mind, though, those units have to agree. H has got units of joule seconds. C has got units of meters per second, which means wavelength has to have units of meters. Okay, pay attention to those units. All right, so what blackbody radiation is showing us is that this matter can emit light when heated, and that color of light is going to be associated with a certain energy. All right, next up, the photoelectric effect. Photoelectric effect is going to involve something called photons. We can think of photons as little packets of light. Okay, we could almost think of them as little particles of light. So when we talked about brightness, when we talked about amplitude, we can almost relate that to photons. If you have more photons coming at you, that light may look brighter. Now, energy associated with one photon, one packet of light, that energy is going to be equal to Planck's constant times frequency. Okay, it's what we saw before with blackbody radiation. Now, how do we see these photons? How do we determine this? Well, it comes from that photoelectric effect. With the photoelectric effect, what they did was they took an evacuated chamber, they put a metal plate inside it, and they also had a metal rod across from that metal plate, but they weren't in contact. And what they did was they shined light on this metal plate, and they saw that they got current flow between the metal plate and this metal rod. Even though there wasn't any contact between them, they still had current flow. Well, in order to have current flow, you have to have electrons moving. So what they came up with was this idea that the light coming in, if it had a sufficient enough energy associated with it, could knock electrons off of this metal surface, cause them to move through the chamber and hit that metal rod. Thus, we were getting current flow. What that told us was light must have some sort of particle property associated with it. That electron has a mass, although it's a small mass, it still has some sort of mass. So in order for that light to knock that electron out, it had to have some particle properties associated with the light. What this helped us determine was that light itself is going to have properties of both waves and particles. Right? It's going to be something called the dual nature of light. So light is a wave. Well, we see colors coming out. Those colors are associated with wavelengths of light. That's proven by the light we see. It's proven by the blackbody radiation that we talked about. But we also can think about light as a stream of photons, these particles of light, these packets of energy, something that has some sort of physical means to knock an electron out, which was proven by the photoelectric effect. Okay, so that's what we're thinking about dealing with this dual nature of light. Now, let's look at calculating some of these energies. Okay, let's say we have a laser. Laser is just going to be an instrument that produces a high-intensity monochromatic light. It's a very specific wavelength of light. Now, we have different types of lasers, and they're used for a lot of different things. So what we're going to do, we're going to calculate the energy associated with one photon of the light produced from various lasers. So we have a carbon dioxide laser, which has a wavelength of 9.6 micrometers. That's going to be used in industry for cutting and welding. Okay, well, what's the energy of one photon of that light? So since I'm given the wavelength of the color of the laser, I'm going to use my E equals hc over lambda calculation to calculate energy. So H is at 6.626 times 10 to the negative 34th joule seconds. C, speed of light, is at 3.00 times 10 to the 8th meters per second. And then my wavelength has to be in meters for all my units to cancel out properly. So I'm given it in micrometers, so I need to get it in meters, so it's 9.6 times 10 to the negative 6 meters. All right. Plug all those in, I end up with 2.07 times 10 to the negative 20th joules. So one photon of that light coming out of that carbon dioxide laser has 2.07 times 10 to the negative 24th joules associated with it. All right, let's look at another laser. So let me take an argon fluoride laser. It's got a wavelength of 193 nanometers, and it's typically used for eye surgery. Well, in this case, plug everything in, make sure my wavelength's in meters, and end up with 1.03 times 10 to the negative 18 joules. All right, let me look at another laser. This is just going to be a green diode laser with a wavelength of 565 nanometers. Laser used in a laser pointer. Plug everything in. I get my 3.51 times 10 to the negative 19th joules. So these are all energies of one photon of light for each of these different wavelengths. So just to summarize these, the carbon dioxide laser, which was used for that welding and cutting, ended up with 2.07 times 10 to the negative 20th joules. The argon fluoride laser, which was used for eye surgery, ended up with 1.03 times 10 to the negative 18th joules. And the green diode laser, which is used just for laser pointers, ended up with 3.51 times 10 to the negative 19th joules. So looking at all these, which one's got the largest energy associated with it, and which one's got the smallest energy associated with it? Well, the largest energy is with the argon fluoride laser. That's the one used in eye surgery. Smallest energy was a carbon dioxide laser, which is what was used in that cutting and welding. Well, why would the lower energy laser be used for cutting and welding? Well, the thing that's not taken into account here is how many photons we send out over a given amount of time. All we're looking at is the energy associated with those photons. So with the argon fluoride laser, we want a high energy laser light, but we're not going to send as many photons out. So the overall energy used isn't going to be as great as, say, the carbon dioxide laser, which is going to have a lower energy per photon, but we send a lot more photons out. Okay, so it's not just their energies, it's also how many photons we send out. All right, so let's look at another example of this that's going to relate this photons and energy. Let's say we have a human eye. And with the human eye, let's say the optic nerve in it needs a minimum of 2 times 10 to the negative 17 joules of energy to trigger an impulse so that we actually see the light that we're shown. So let's say we take red light, which is at 700 nanometers. How many photons of that red light are we going to have to see in order for us to even register that we're seeing that red color? Well, we need to know the energy associated with each photon of light, so plug everything into my calculation, and I end up with 2.84 times 10 to the negative 19 joules for 1 photon of red light. Well, now it's just a matter of doing a unit conversion. If I need that much energy, 2 times 10 to the negative 17 joules, and I know for every 1 photon I have 2.84 times 10 to the negative 19 joules, well, when I do that, I end up with 70.4 photons. So how many photons do I need in order to see that light? Well, it's not 70 and it's not 70.4. Okay? I can't have fractions of photons. Remember, these are energy packets. Okay? These are acting like particles. I can't have a fraction of a particle. So because I'm at 70.4 photons, I'm above the 70, in order to even see this light, I would have to at least have 71 photons strike the eye. Okay, let's look at a different wavelength of light using this example. Alright, so let's look at blue light, which is at 475 nanometers. Calculate how much energy is associated with 1 photon. Take my minimum amount of energy, convert that to photons, and I get 47.7 photons. So what's the minimum number of photons I need? Well, it'd be 48 photons. Okay, so for red light, I need 71 photons to strike my eye. For blue light, I need 48 photons to strike my eye before I can register it as red or blue. So we've talked about the energies, we've talked about the basics of electromagnetic radiation, we talked about black body radiation, photoelectric effect. Now let's get into spectra. All right, we've already talked about one form of this before, which was this continuum spectra. Okay, where we took that white light, put it through a prism, we got that rainbow or all the colors of the rainbow out. That was a continuum spectra. Well, now what we can look at is something called emission spectra. And with emission spectra, what we can do is we can apply electrical energy or a current through gas atoms to cause them to emit light. Okay, and this is the third thing that we're going to talk about relating this concept of properties of electrons and electromagnetic radiation. If we pass electrical energy through these gas atoms, it's going to emit light. All right, when we look at this, though, for individual elements, we get these emission spectra. All right, with emission spectra, we're going to end up with monochromatic light, mono meaning one, so one color light, and we're going to end up seeing what we call line spectrum for these elements. So let's say I take a tube that's got hydrogen in it, I pass that electrical current through that hydrogen, it emits light, I take that light and pass it through a prism, just like I did with the white light. So now all the colors that come out are only the colors associated with the element hydrogen. Right? So you can see here we've got basically 4 colors coming out. In the line spectrum, you notice it's not a continuous color transition, it's got very distinct wavelengths of light and colors of light that are showing up. When we combine them all together, that's the light we'd see coming out of this particular tube. What this leads us to, though, is this concept that we're going to get into later on about how there's energy levels within these atoms and how those energy levels are going to contain those electrons. These very specific wavelengths of light are going to help us measure those energies associated with those energy levels in the atom. Okay, so this is an emission spectrum. It's a line spectrum for hydrogen. Each individual element, though, is going to have a different line spectrum associated with it. It has different wavelengths of light that are going to come out. Right? Helium, you can see, has 3 blue, a yellow, an orange, and a slightly less intense orange, whereas barium has even more colors associated with it. Each one of those colors and their associated wavelength is going to help us determine energy levels within an atom of those specific elements. So each element has its own line spectrum. Now, just for comparison, though, keep in mind, line spectrum, you can have those black areas where there's no color in between the different lines. Whereas the bottom with the white light, that was a continuum spectra. There's no stopping point. It's a continuous transition from one color into the next. Okay, that's the difference between the two. Okay, now, when we look at those line spectra and we look at those elements are going to have different line spectra associated with them, which is going to end up having us see different colors for different elements. Okay, obviously, we can't have a different color for every single element. Some elements are going to have similar color schemes when we look at it in the flame test. But when we break it up into line spectra, every single element should have a slightly different line spectra. So we could actually use that to identify what element we're dealing with. And just the last thing to note, little fun fact on this, if we think about fireworks, fireworks contain metal salts. When the explosion goes off, those metal salts are heated, they're converted to the gas phase form of those metals, and then the electrons in those atoms are thermally excited, they fall back down to a ground state, they emit light. That's why we see the colors of light that we see in those fireworks. It's just got a whole batch of different metal salts. It's got gunpowder and other explosives in there to provide the energy to cause these metal salts to get excited and emit their light. Okay, but it's really these metal salts that are causing the different colors of light that you see in those fireworks. All right, but that's going to be it for electromagnetic radiation and spectra.